our last section in chapter 7, I want to take a moment to consider these two classic Corvettes. Those are some nice cars. Now there's a difference between them. One of them is souped up, and so it goes from 0 to 60 miles per hour in 4 seconds, versus the classic 58 Corvette goes 0 to 60 in 8 seconds. So besides the fact that one car is pink and the other is teal, what's the difference between these two cars? Well, notice they both go 0 to 60, so it's not that they have different speed limits, at least not in what's been presented here. But they're able to go from 0 to 60 in very different time intervals, right? So they have the same speed change. The souped up one is in a much smaller time interval, so it's a much larger acceleration. But why does it have so much more acceleration? What's driving that additional acceleration? Well, if we take a look at the energy, right, we know that they have the same change in energy over time. They can both go from 0 to 60 miles per hour. So you could calculate the change in kinetic energy, it would match. So in other words, both cars are doing the same amount of work in getting up to highway speeds. But one of them does it in much less time. And so in terms of energy, the quantity that we'd talk about is power, right? That the pink Corvette has much more horsepower than the teal Corvette. So power, we're going to see, is the work divided by the time interval it takes to do that work. So if you're able to do the same amount of work in less time, then you have more power, right? So let's take a look now at the math behind this. So power is the time rate at which a force does work. A force does work W in a time delta T, and so the average power due to this force is equal to the work divided by the time interval. This is what we'll often use to calculate power. We'll often assume that average is the same as instantaneous. So the instantaneous power at one particular time is where we can shrink that time interval down to an instant, and it just becomes a derivative. Power is the derivative of work with respect to time. Now, what is the unit of power? Well, I believe it or not, just told you the answer. Let's take a look. So we have the units of work, which are what? They're joules, right? Work has energy units, which is the joule, great, but it's the unit of time. Time has units of seconds, so joules per second. And 1 joule per second is by definition equal to 1 watt. What? Yes, exactly. That is exactly it. So it's spelled W-A-T-T, watt, and it's written with a capital W, which is very unfortunate. We just don't have enough letters in the English language. So you need to use context to note when it is a unit, that's going to be different than work, which is a quantity. So those are parallels. There's no resolving them. You just, again, need context there. So 1 watt is equal to 1 joule per second. So that's a handy one to remember. And because of this, you can write work or energy, because remember, work is just the change in energy. And we're going to see that more explicitly in chapter 8, that we'll calculate the power with just the change in energy over the time. So either of these are a good way of thinking about the power that is being happening. So we can write our work or energy as power times time, right? If we solve for work here, we can multiply by time. We get that work is equal to power times time. And an example of this is the kilowatt hour, which you've probably seen if you've ever looked at an electric bill. Your electric bill says you used 100 kilowatt hours, right? How is that a unit of energy? Well, remember a kilowatt, that would just, kilo is a prefix. So we could write this as kilojoule per second, and then it's times an hour. And we could cancel the hours and the seconds if we just had the right conversion factor, right? We're multiplying by time and dividing by time. So those will cancel out and we'll be left with a unit of energy. So little did you know, but you had SI units on your electric bill. Power, incidentally, also highlights your light bulb when it says it's 60 watts. That's not saying how much energy your light bulb will use. It's telling you how much energy per second it will use. So that 60 watts says that in 1 second, that light bulb will use 60 joules of energy. Isn't that cool? It's all around you. More efficient bulbs like LEDs are able to give a brightness equivalent to a 60-watt bulb, but only use, 4 watts or something like that. So a fraction of the energy cost to get the same brightness, which is pretty nifty. Seems like a bright idea to me, or at least a very powerful one. All right. Another way we can write power, that we can calculate it, is if we take that instantaneous power definition, that's the derivative of work with respect to time, and then plug in our work equation as force times cosine the angle times x, and then it becomes dx. Assuming that we have a constant force, that's not going to be changed by the derivative, and so the cosine of the angle is not going to be changed. So the only thing that will change is that x, the displacement. So then notice we have a dx in the numerator and a dt in the denominator. If we regroup them, we have dx dt. We've heard of dx dt before, right? This is just our velocity. So we have force times velocity times cosine of phi, the angle between the force and the velocity, which just matches our dot product. So this gives us another way that we can calculate the power. If we know the force and the velocity, we can get the power as well. So that brings us to the end of chapter 7. Hopefully you are all energized about it. Don't worry, there's more energy to come in chapter 8. So stay tuned, stick around. It's going to get even better because physics always does get better. Keep it real, yo.